Thank you very much for the invitation, and it's a pity I can't be there in person for the workshop. In this talk, I would like to share work on the energy transfer in the ocean across scales, and this work is in collaboration with Oliver um, from Croft, Drew from Colombia, and Rafael and Fabio from Lyon. And we consider a turbulent ocean problem because, in the ocean, the characteristic scales can be very large and very small. The largest scale can be thousands of kilometers, and the smallest scales can be centimeters. So there's a big range of degree of freedom, and there could be a strong turbulent motion. And because the system is highly nonlinear, the motions at different scales they interact, and when they interact, they could transfer energy between scales. So our question today is to ask in the ocean, at each scale, in which direction energy transfers, whether the energy transfer from large to small scales or from small to large scales. And this is important for our understanding of the ocean flow. Like we want to know the transport problem, and if we want to do modeling, for example, if we do numerical model, we would like to take a grid from to the ocean, and so we have a finite resolution. Everything smaller than the grid cannot be resolved, but there is a nonlinear interaction between the unresolved motion and the resolved motion, and the unresolved motion could be important. They could lead to strong dissipation, or they could give energy to the resolved motion. So this will be important for the modeling. So and if we have a good model, we can do more research on weather and climate and many other things. So our question now is, how do we know energy transfer across scales in the ocean? And how can we obtain this information from measured data? And how can we quantify this? We borrow ideas from fluid dynamics, the classic turbulence study. For example, in 3D turbulence, 3D homogeneous isotropic turbulence, there is a classic picture by Richardson, the forward cascade. We have energy continuum vortices. They tend to break into smaller vortices, and the vortices break into even smaller ones. And this process continues until the small vortices reach the scale of dissipation, then energy starts to dissipate. So in this picture, energy transfer from large to small scales. And Kolmogorov in 1941 brought up a very important theory, so-called K41 theory. It's about he derived the relation between the third order structure function. Here, the third order structure function is if we have a velocity field, we can, for example, pick 2 points, 1 and 2, and at 2 points we have velocity u1 and u2. We can define that dot u as a velocity difference. If we calculate dot u to the power 3, we take average over bar, we can find the equation, the Navier-Stokes equation after average will give you the third order structure function is proportional to the epsilon, which is the energy flux across scales, and r, which is the 2-point distance. And the coefficient is minus 4/5. And this one is a number calculated from the equation. So with this expression, this is more than dimensional analysis. You can have the coefficient. So if you have measured data, you can calculate energy flux from your experiment. And this is for 3D turbulence. And there is another also classic turbulence, homogeneous also isotropic 2D turbulence, but the scenarios are different. In this system, energy transfer from small to large scales, but in the energy inertial range, you can also have third order structure function proportional to the energy flux epsilon and also the 2-point distance r. However, the coefficient is different. In 2D, the coefficient is 3/2, and it's positive. There's a sign difference between the two cases. So people can use this the sign of the third order structure function to determine the direction of energy transfer. And this idea was taken by Chu et al. 2022. They use a ship ADCP data in the ocean. They cut these data into 5 regions, And in each region, you have velocity at different locations, so you can calculate the third order structure function. And they plot the third order structure function against the 2-point distance r. The blue are the negative values, and the red are the positive values. Sorry, the blue is the positive value, the red is negative value. So you can see from these 5 figures, they are both they are all have blue and red colors. So there's a positive and a negative third order structure functions. So they have a conclusion. There is a bidirectional energy flux in the ocean. At some scale, energy transfer from small to large, and at some scale, energy transfer from large to small scales. So I would like to mention calculating and transfer, you can use many other methods, and which method to use depend on what data you have. For example, in this Alui paper, they use a filter because they have numerical simulation. In the numerical simulation, you can easily calculate horizontal derivatives. But for the measured data, if you have very sparse data, the horizontal derivatives are very hard to calculate without introducing more error. Also, you can get relation from the third order structure function and the filtered energy flux by also a filter. But this filter, this kernel convolution, you need to integrate domain. The whole domain is the whole space. This is doable if you have a numerical simulation, but when you have a measured data, this the convergence of the integration may be questionable. So in this work, we stick ourselves to the third order structure function method. However, the classic third order structure function method has a little flaw. As we just mentioned, the third order structure function in the initial range scales like r to the power 1. However, if we look at Chu et al.'s data, we can see this dashed line is r to the power 1, but there is a big range of data. The third order structure function does not scale like r to the power 1. This means if we want to directly apply the theory to the data, it's questionable. So what we do is we go to the original equation, try to see if we can get a better expression. So we go to the correlation equation, this is so-called Common-Horace-Morton equation. And if we take a Fourier transform of this equation, we get the equation for energy spectrum. So we have this relation between the spectral energy flux and the third order structure function. This overhead is a Fourier transform. And from this relation, if we assume 2D, we assume isotropy, we can get a relation between the one-to-one relation between the energy flux and the third order structure function. And if we consider a simple scenario, there is a energy injection at one scale or one wave number, and they transfer to both large and small scales simultaneously. The go to large scale, the quantity is epsilon u. Go to small scale, the quantity is epsilon d. So we can express this energy flux as a Heaviside function. So you can plug in this flux expression into the relation to obtain the third order structure function. And so this relation is what we are going to do to analyze our measured data. Before we do the data analysis, we can check in the small and large scale limits. This new expression recovers the classic limit for the 2D and 3D scenarios of energy transfer to downscale or to small and large scales. So the data we use is drifter data in the Gulf of Mexico. We use summer data GLIDE and winter data later. So in this picture, we can see the black dots are the initial points of the drifter, and the colored curves are there. We can see this is a very non-uniform data, so it's very hard for us to do a horizontal derivative estimation. So in this, to deal with this data, we choose to use a third order structure function. So what we do is we use our new expression, a linear combination of our previous expression. We assume there could be many scales that inject energy into the system. There's IFI, and at each scale, there's energy injection magnitude epsilon, and this is epsilon u is upscale energy flux. So we have the location of drifters at different time, so we can calculate the velocity. When we can calculate the velocity, we can calculate the third order structure function. So in this expression, we have this v, the third order structure function, which comes from the measurement. We have the r, which is a 2-point distance. We can also obtain from the measurement. Then we can fit this expression to get our epsilon u and epsilon i. So our result is after we get the energy injection and upscale energy flux, we can reconstruct the energy flux. Here in summer and winter, we can see the energy flux. This curve is the energy flux in the spectral space. When the value is negative, it's upscale energy flux. When the value is positive, it means downscale energy flux. So in both cases, we can see there's a upscale energy flux and the downscale energy flux. With this information, we can also know at which scale the energy inject most. These scales are where the energy flux change most. So here we can see there's a big jump in the energy flux, so there must be some strong energy injection. And here is also a big jump in the flux. There's also a energy injection. So compare with these two results from summer and winter, we can see there is one energy injection scale, large energy injection scale, which is almost unchanged between summer and winter. This scale is around 50 hundreds of kilometers. 50 kilometers. And however, we can see there is also another small scale energy injection scale. In the summer, the scale is around 1 kilometer, and in the winter, this is around several kilometers. And we think this seasonality is a result that the kinetic energy source in the surface ocean could come from the barokinetic instability. This 50 kilometer corresponding to the deformation radius of the ocean depth. This ocean depth does not change with season. This 1 kilometer and several kilometer corresponds to the mixed layer depth, the deformation radius of a mixed layer depth. So in the winter, mixed layer depth is much deeper compared with summer. So this energy injection scale is much larger. So with this result, we can have some implication on modeling. For example, if we have a numerical model which has a resolution like 100 meter, in this 100 meter, we can see the energy transfer from small to large scale. Oh, sorry, from large to small scales. So the subgradient for the motion acts as energy dissipation. So we can use some simple model like a Smagorinsky model to capture the energy dissipation. However, if you have a numerical simulation like climate model, your resolution is like 50 kilometers. At 50 kilometers, the energy transfer is from small to large scale. This will be a very challenging problem because the subgraded motion inject energy to the resolved motion. So at the grid scale, you need to inject energy into the system. Viscous model is not reasonable. So to give a quick explanation why there can be energy transfer to both large and small scales, we think the motion of the wave is important. So here we take one example by the interaction of near inertial wave and the QG mean flow. This is just an example. I just want to show the conserved quantities are important. For the wave system, one important conserved quantity is the wave action. And this wave action usually have less horizontal derivative compared with other conserved quantities, for example, like this energy, and also there's a potential entropy. If there's no wave, we have energy and the potential entropy conservation, and the system will have a QG turbulence, and the system behaves like 2D turbulence, energy transfer from small to large scales. However, if we have strong wave, the total energy is dominated by the wave, which has a gradient in the wave in front of the wave amplitude. And also wave action is important because we consider a wave strong scenario. In this case, using the same argument like 2D turbulence, we can conclude that the energy here, because it has a more horizontal derivative, it will transfer to smaller scales. So if we have strong wave, the conservation of energy and the wave action will tell you the energy will go from large to small scales. So now in the ocean, we have a combined system of balanced flow and wave. So there could be energy transfer in two directions. So in summary, we obtained a new expression for the isotropic turbulence and for the third order structure function. And this expression can capture energy injection scale and can capture the bidirectional energy transfer. Using this expression, we analyze the ocean data to justify that the kinetic energy transfer in the ocean can be bidirectional. And this could be a good thing for us to do parameterization. This is what we are doing now. And also we have a conjecture that the downscale energy flux could be a result of a wave. And this is also something what we are doing. We are trying to decompose the the wave and the mean effect in the third order structure function to see different components impact. And also, before I stop, I want to say there are many defects of the current work because we use a isotropic system. We do not consider anisotropic effect, but in the ocean is anisotropic, and we ignore the effect of rotation and stratification. And also, we didn't see anything about submesoscale because it's very hard to make a distinguish between waves and submesoscales. And that's all. Thank you very much.
Yeah, we can take questions now. Questions?
Did I? Oh. Should I share again? Oh.
If you can just put on your slides, that's fine. Now we are not seeing the slides.
Can you see the slides now?
Yes. Yes. Okay, we have the first question.
Hi, just a quick question. With the third order structure functions, how do you know when you have enough sampling? You know, with the data, you don't have enough data to take derivatives. I understand that. That's so you go to the third order structure functions and you can calculate something, but how do you know that you've sampled for any delta X, for any R, you might only have 2 or 3 float pairs or something.
Oh, thank you for the question. We check this by looking at the PDF of the structure function. What we see is that the PDF of .u the tiles tends to 0, so we believe we have enough data. And also I want to say in this third order structure generation, you can see we do not have many points. In fact, this one, for example, this 10-kilometer point collects all the data from like a 5-kilometer to 20-kilometer distance. So we have a lot of data.
Can I ask, so when you see this forward flux of the energy from those observational data sets, are those caused by waves, linear waves, or are they unbalanced flow components that are not waves?
That's the thing we don't know.
Did you look at the dispersion relationship? Did you have data to look at that?
I think we do not have enough data to do that. We only have drifter data. It's a Lagrangian particle. Okay. But we do not have a field of data. We only have a very sparse points.
Right. Okay. Thanks.
We also have one question online. If you could suggest any material to learn turbulence theory in more detail, you can please put it in the chat.
Okay, I can type someone.
Thank you. More questions? Seems like there is no more questions. Then thank you very much. You have one question? There is one more.
I wonder what happens if you go to larger scales when you have zonalization and beta effects and Rhines effect and so on. Would you see this in your structure function?
First, we don't have data, and second, if we we tried this using numerical simulations, even in the beta plane, because we take a angle average. So even we have a beta effect, we can also extract the isotropic part component. And using this isotropic component, we can see there is an upscale energy flux in the beta plane turbulence.
Oh, so then there is no effect on the structure function, or is there?
No, the structure function, in fact, comes from the relation. In fact, it's the exact relation between the third order structure function and the spectral flux, and this is exactly the nonlinear term, the advection term.
Yeah, but I suppose the dynamics are different if you have.
Yes, even though you have different dynamics, as long as the direction of energy flux is the same, you get the same energy third order structure function.
Okay, thank you.
Okay, now we thank you.
Thank you very much.